I will give you extra credit. You got to email me and remind me, though. Give me 1 second here. All right. Sorry, the dogs have decided that they're going to contribute to class today. So, all right. What did we learn last time?
Probability?
We did learn probability. And what did we learn about probability?
About how to use unit normal tables?
Yes, a unit normal table. And somebody else, what is on those unit normal tables?
It's pretty much all the z-scores, all the positive z-scores, and pretty much the percentages that either the body or the tail are going to have at that corresponding z-score.
Yeah, exactly. So you're going to have the probability of a z-score above that, a z-score below that, and the probability of the z-score, or excuse me, the probability that you get a z-score between the mean and that z-score of interest. To it. I have to be right back. I have to let the dogs in, and then we'll continue. Sorry about that. The dogs have decided that every squirrel outside presents a threat today. So hopefully they'll finally shut up. It has not happened so far today. All right. So yes, we learned about the unit normal table. We learned about the probabilities. What else did we learn?
Binomial distribution.
Binomial distribution. Okay. And what is a binomial distribution?
It's pretty much, it's harder for me to describe, but it's like we're looking at, I guess when we have two different possibilities or two different probabilities that we're looking at.
Yeah, so two different outcomes for anything. Yeah. And so exactly like Caleb said, so we're, the word binomial, bi meaning two, is indicating that we have two different possible outcomes, right? So you think of a coin flip, you have heads or you have tails. When you think about the any sort of question on an exam, on a multiple choice exam, you have two different options, right? Correct or incorrect. And so, all right, this isn't indicating, are y'all seeing the PowerPoint right now, or are you seeing my other screen?
PowerPoint.
Okay, good. Zoom has poor human factors. You also take my human factors class, and then we can talk about the issues with it. But cool. So any questions about what we covered last time?
I had a question about when we're doing binomial distributions, and pretty much like when we're using our x value and we use the lower limit as our x value instead of the actual number that we're trying to find. I was basically just trying to confirm. So we use the lower limit if okay, let's say the question is asking if we have 20 or more, what's the probability that 20 or more are going to have the right score? Would we use that's when we'd use our lower limit, right? If we're using if we're trying to find
Yes.
That actual number and everything above it.
Correct. Yeah. So you would use the lower real limit for something like that. So if we wanted to know what's the chance that you get a 14 or higher, now again, like I said last time, that's going to be a little amorphous in the sense that I think you could reasonably make the argument that unless it's specified to use the real limit, that the question in that case wouldn't be asking for the real limit. But if there is a case wherein I want you to use the real limit on the exam, I will tell you to use the real limit. Otherwise, you could do the real limit, or you could do or you could just do the actual number I asked about. But I will specify on the.
Okay. Sounds good. Thank you.
Yeah, of course. Any other questions? Nancy, I am posting the slides as we speak. Thanks for the reminder.
Would you tell us which limit to use, whether it's the upper or the lower one?
So in any case wherein I'm telling you to use the real limit, you would have to infer. So if I'm talking about using the real limit, for example, if you got 14 or more correct on the exam, excuse me, that would be the lower real limit, because I want to know what is kind of essentially the lowest value you could get to get in accounting for that actual probability. If I said, what are the chances that you get 14 or less on the exam, then you would use that upper real limit of 14.49. Andrew asks, what time is the exam going to be posted? That will be posted at essentially 12:01 a.m. on the day of the exam, and it'll close at 11:59 p.m. Any last questions? All right, well, if you do have any, go ahead and type them into that chat box or unmute yourself. Here is your fun fact of the day. Bethlehem, Pennsylvania rings in the new year every year by dropping a 200-pound illuminated Peeps chick. If any of y'all have been down to Mobile, they drop a moon pie for New Year's. So I like those kind of unique traditions. All right. So today we are talking about the distribution of sample means. And so in chapter 7, we talked about extending the concept of the z-scores and the probabilities to samples of more than one score. To accomplish this, you're going to have to know about what we kind of refer to as all the possible sample means. Right? And so if you think about taking a population distribution and pulling out a certain number of people from that population, you're going to get variability in what that actual mean is, right? I've already talked about this a little bit before in this class, that no two samples, even if pulled from the exact same population, are going to have the exact same mean. And I'll show you an example of that in just a little bit. Oops. So once this distribution is identified, you can then calculate a z-score for each sample mean based off its location and then understanding its probability. And so let me just draw this for y'all here. Give me 1 second. All right, so let's think about having a population distribution. And let's say this is just the, let's say, height of everybody in the world. This is the population for that. If we were going to be pulling people from this population, let's say we had a sample of 25 people. And so we're going to get a couple here in the middle. We may get, ones kind of near the tail. But you can see how we've now pulled out our sample from the population in here. If we were to then put all those people back, we would then do, let's say, another sample. And you can see how there's going to be a lot of overlap, but it's not going to be the exact same. And so wherein the mean for the black dots might be here, the mean for the red dots, let's say, is down here. So they came from the same population, but they represent very different, well, they're not very different, but they represent different means, right, of the sample. And so what we're talking about today is, pulling out these individual data points for a sample and then evaluating how representative each one of these samples is of the known population. And so the distribution of sample means is defined as the set of means from all the possible random samples of a specific size from a specific population. So if we go back to that example I just drew here, and we look at the fact that each one of these has a different mean, and let's add another distribution in here. You can see that we're going to get another one. And what we're doing for the distribution of sample means is taking all of these means and we're plotting that into a new distribution. And so you can get from this distribution the what's known as mean of means, right? And so you've got, if we go back here, so red. So let's say our red mean was here, our black mean was here, and our green mean was here. And you're doing this for all sorts of samples pulled from this population. You then get this distribution in here. And it's going to be indicative of what are the actual sample descriptives that we should expect for here. And you're going to have usually a smaller variance in here than you're going to have in the actual population. Now, why would that be? Somebody give me a guess as to why that may be the case.
You're asking why would there be a smaller variance?
Yeah, why would there be a smaller variance for this distribution of sample means rather than the distribution of the population?
Because you're taking from a smaller amount of people than the whole population?
Not quite.
Is it because those were already averages that are all representing the same data, so they should have closer values towards the same mean?
Yeah, and so because you are plotting these means, you are already kind of washing out any of the extreme values. A single extreme value like you have, or a couple over here, like you have in the population, are going to distort kind of the look of your population. However, as a function of just being averaged, these kind of outliers are brought back towards the middle as we look at the actual average. And so because you are taking these averages, which are accounting for those extreme values, but are not going to have as extreme values, when you plot them, you're going to have just a smaller variance like represented here, right? So just think about it. Is it more likely to find one person who is 7 feet tall or pull out 100 people whose average is 7 feet tall? Well, it's a lot more likely to pull out one person that's 7 feet tall, right? And so that's all we're doing in plotting here is essentially establishing what is the variance associated with all of the means from that population. So the mean of the distribution of sample means is called the expected value of the mean. All right, so that mean of that means distribution is the expected value of the mean. The standard deviation of that new distribution of means is called the standard error of the mean. And so whereas we know how to calculate the standard deviation that we have been using up to this point, the standard error of the mean, excuse me, I tend to think that this is the easiest over here on the left, but taking that standard deviation of that population, we know what that standard deviation is. Sorry about the dogs. I now remember why working from home isn't the default standard for every profession. But so you're taking that known standard deviation and dividing it by the square root of the n of that sample. So if you sampled 100 people, you're taking the square root of 100, which gives you 10. And that gives you that standard error of the mean. The shape of the distribution of sample means tends to be normal if the population from which the samples are obtained is normal and the sample size is roughly 30 or more. And so there are some critical assumptions that are made when using what are known as parametric statistics, like we're going to be covering this semester. And one of the assumptions is that the sample you're pulling from has a normal distribution. And to get that normal distribution, you usually need a substantial enough sample size. And so the standard varies a little bit, but roughly about 30 is going to be that assumption. So like I've already said, the sample means are variable, right? And so if you take 2 or more samples that are selected from the same population, the 2 samples will probably have different means. And so to illustrate that, don't worry about how I am doing this here. But what I've done is told Python here to take a sample from a population whose mean is 10 and whose standard deviation is 2. And I've told it to just give me 40 samples, right? And you can see how variable these samples are, right? You're going to have some extreme samples, like one that has a mean of 3.86, and others that have a mean of 14. But these are all pulled from that same population. And so just by chance, you're going to get some of these extreme values here that are not necessarily representative of a population whose mean is 10. However, with getting enough samples, those means should, quote unquote, pile up around the population mean. That distribution is going to form, at least usually, a normal distribution with an expected value of that population mean. And again, any individual sample that you pull is not going to be identical to its population mean, which is indicative of some error, right? So if we go back to this example here, we know that the population mean in this case is 10. And you can see for any individual one of these samples, you're not getting exactly 10. You've got one that's pretty close, but there's going to be some variability. But if you were to average all of these, you would probably get something very close to 10. All right, so any individual point is not going to be identical to the population, but the sum of each of those means is likely going to give you something fairly close to that population mean that you're pulling from. And so the standard error, again, just like the standard deviation, is providing a measure of the standard distance between the mean, the sample mean, and the population mean. I'm going to pause real quick. Who has questions about that?
So if the expected value of mean is the mean of the sample means, then what is the mean of means?
That's the same thing.
Oh, it's the same thing. Okay, cool.
Yep.
Okay,
Good
that makes
question.
sense now.
What other questions do we have? All right, well, I'm going to go ahead and move on. If you do have any questions, let me know. And so here is just a representation of what we've already been talking about. Right? So you've got your distribution in here, and we're going to pull people from this distribution. And so over here on the left-hand side, you have the distribution for means if you only pulled one person out of this, right? So if you only pull one person out of this to represent your mean, your standard deviation is going to be equal to your standard error, right? Because all you're doing when you're pulling just one person out at a time is recreating that distribution. So when your sample has an n of 1, your standard deviation is going to equal your standard mean, right? Because just think about it conceptually. If the equation for standard error of the mean is the standard deviation over the square root of n, if 1 is n, the square root of 1 is just 1. However, you can see what happens as we start to increase our sample size, right? And so for that same distribution, that same population, if we now take 4 people to calculate our mean, our standard error is going to be 20, which is the standard deviation for this population up here, divided by the square root of 4, which gives us 2. 20 divided by 2 gives us 10. The mean should still stay the same, But as you increase that sample size, you start decreasing that standard error of the mean. And again, if we go to pull from that same distribution over here, but now we're pulling 100 people for every individual mean we're now going to plot, that standard error of the mean goes way down to just 2. Right? And again, this conceptually makes sense. If you've only got 4 people, it's going to be a lot easier to have a more extreme value for your average. If you've only got 4 people, finding one person who is 8 feet tall is going to throw your average height way off, right? But if you've got 99 other people, that 8-foot tall person is not going to throw that mean off all that much, which is going to reduce the amount of variance in this distribution of sample means. And so within the distribution of sample means, the location for each sample mean can be specified by a z-score. And this equation is almost identical to what we've been doing. It is the same conceptual equation. But now, instead of x, we have the mean, so the sample mean. We're going to subtract the population mean. And now, instead of dividing by the standard deviation, we're dividing by the standard error of the mean. Right? So it's again still the conceptual equivalent. What do we care about? What is the population truth? What is the standard deviation of what we are pulling from? And we'll do some examples of this in just a few minutes. So as with z-scores before, a positive z-score indicates that the sample mean is greater than the population mean. A negative z-score means that the sample mean is smaller than the population mean. And that numerical value of the z-score indicates how far away from the population mean the sample mean is. Again, measured in terms of standard error, right? So when we were dealing with the population before, if you had a z-score of 2, that meant you were just 2 standard deviations above the mean. Here, if you have a standard error, or excuse me, if you have a z-score of 2 when looking at the distribution of sample means, what that means is you are 2 standard errors above the mean. And so again, the standard error is still the same conceptual idea as a standard deviation, but we give it a different name because instead of looking at the standard error for each individual data point, we're looking at that deviation for the sample from what would be expected given the population. And so if we look at this population here, if we have a mean of 500, and we want to say, what is the middle 90%, or excuse me, 80%, we need to know, okay, what are the z-scores that correspond to having 10% in each tail? And that just happens to be that 1.28. So again, if we go look this up on the unit normal table, let me pull it up. All right, we want to know what corresponds to 10% in the tail for each direction. We're going to scroll, 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 and 1.28. Go back. Yep, positive 1.28, negative 1.28. So again, this is just kind of a refresher of what we did before. What we're doing today is going to be almost identical to what we did last time, except for that extra little step of calculating that standard error of the mean. And because there are certain fundamental assumptions which you can't violate when you're using that unit normal table, the distribution of means is going to be normal for the probability and sample means. That means the z-score you obtain can be used to get that probability just like we did before. And so again, the only difference between what we're doing this time is that we have to consider the sample size and that standard error of the mean rather than just the standard deviation. Excuse me. All right, so we've already gone over this, so let's just go ahead and skip that. So like I said, the standard error measures that standard distance between the sample mean and that population mean. Therefore, that standard error of the mean provides a measure of how accurately, on average, a single sample mean is representing its corresponding population mean. Right? So last time we talked about the probability of an individual data point. What is the probability that this data point, or that you're going to get a data point here or higher, for example, given this known population? Now we're saying, what is the probability that you would get this this sample mean, given everything we know about the population, if the sample is in fact representative of the population? So again, because the standard error of the mean is inherently reliant on this sample size, right? Because it's just standard deviation divided by the square root of the sample size. Again, if you have a sample size of 1, the standard deviation of 10 in this case is going to be equal to the standard error of the mean, 10. If you have 4 people, the standard error of the mean is going to be the standard deviation divided by the square root of 4, or 10 divided by 2. If you have 9, it's going to be standard deviation of 10 divided by square root of 9, which is 10 divided by 3, or 3 1/3, 3.33, and so on. Right? So again, it's important to conceptually understand why this is the case. As you increase the sample size, you're reducing the chance that any individual outlier, any point way in the extreme of the distribution, somewhere out here, is influencing that mean. All right, questions before we move on to some practice examples? Is anybody feeling overwhelmed at this point?
Yes.
Okay, that's totally normal. Yeah, I normally like to, in non-COVID times, have y'all vote with a thumbs up or thumbs down, but it's hard to do that in this time. So, all right, don't worry, we're going to show some examples. I always find stats is the hardest when you're trying to talk about the conceptual cases rather than actually doing the problems.
Yeah, that's the biggest thing is trying to, not so much as comprehend, but piece together how to actually put that into the actual statistical problem. But then once I see the example, it makes it feel a lot better. It's just more so trying to grasp the hold of that concept.
Yeah, absolutely. All right, so let's move on to some practice examples. Let's just start with converting standard deviation into the standard error. So let's assume a population has a mean of 80 and a standard deviation of 20. What would that standard error be if n equaled 1? Somebody give me the answer.
20.
20. Yeah.
Yeah, exactly, right? So when we think about the equation here, it's just going to be the standard deviation divided by the square root of n, right? And so the standard deviation of 20 divided by the square root of 1, or is 1, that's just going to be 20. What about 4?
10.
10. Perfect. Again, standard deviation of 20 divided by square root of 4, or 2. 20 divided by 2 is 10. What about 25?
4.
Yeah.
Right?
Yep. So standard deviation of 20 divided by square root of 25, which is 5. So 20 divided by 5 is 4. And then what about for 100?
2.
2, exactly. So standard deviation of 20 divided by the square root of 100. Square root of 100 is 10. 20 divided by 10 is 2. Perfect. So when we look that up here, 20, 10, 4, and 2, exactly. So y'all should feel pretty confident now, because all we're doing from here on out is applying what you already know, right, with the z-scores. So once you take that known population standard deviation and that known that known sample size, you're able to get that standard error of the mean nice and easy. This is just regurgitating what we've already gone over. I want to leave a lot of time for examples here. Yeah, I think I just had these out of place. Yeah, so ignore those. Ignore all of that. I mean, you can read over it. It just says the same thing we've already said. All right, so here is another example. Suppose you wanted to predict what range of scores you would expect 80% of the time for a mean SAT score for a sample of 25 people. And let's say we know that the SAT has a mean of 500 and a standard deviation of 100. So let me go ahead and share the iPad again here. All right. So let's talk about some things we know here. So we know let's see, we want the scores for the middle 80%, right? We also know that the SAT has a population mean of 500 and a population standard deviation of 100. And so we are going to take a sample that has 25 individual participants. And we want to know, again, what are the scores that correspond to the 80%, the middle 80% of the distribution of samples that have 25 people? And so what is the first thing we need to do to figure out what those scores would be?
We need our z-score.
Yeah, we need our z-score, exactly. And so to find our z-score, we once again go to that unit normal table like we did before. To find 10% in each tail, because we want the middle 80%. 10%, 10%. We know we want this 80%. So the z-score for 10% in each tail is going to be 1.28. All right, so now we've got our z-score. What do we need to do?
Find the standard error.
Find the standard error, exactly. All right, so we know we've got a standard deviation of 100. Based off of our sample size of 25, what is our standard error of the mean going to be?
20.
20. So we take 100, which is that standard deviation, divided by the square root of 25, which gives us 100 over 5, or 20. Yes, so there's our standard error. All right, and what's the equation we use to find a given value of interest to us with a known z-score?
The x equals is it mean plus z times the standard deviation?
Yeah. So that's the equation we have used up to this point. Again, conceptually, nothing about the equation I'm about to show you is going to be any different. But now we're interested in the mean rather than x is going to be equal to that population mean plus the z-score times that standard error of the mean. So the mean value we have is going to be that mean for the SAT, or 500. We're going to do plus and minus because we want that middle 80%. The z-score, which is 1.28, times that standard error of the mean, which we calculated was 20. So we get 500 plus or minus, let's see, 1.28 times 20, 25.6. So if we add 25.6 to 500, we get 525.6. And if we subtract that from 500, we get 474.4. So we know that these are the two scores which correspond to that middle 80%. So if we go down here, 474.6, 525, oh, excuse me, 474.4, 525.6. So now let's go back to our PowerPoint. Perfect. And there we got it. So again, you know the equation, even before today, you know the equation that you wanted to be using. You know that instead of the standard deviation, we need the standard error of the mean. And once you know that, all it requires is you just plugging in information you already know. What questions do we have about that?
I don't get how you got the z-score.
So the z-score, again, we are looking up in that unit normal table. And so let's open this up. So we know that what we want is the middle 80%, right? So that leaves 20% left divided into the two tails on either extreme. So that means we need the 10% value in each tail. So to do that, we look in this tail column, so this B column, and we scroll all the way down until we get to 10. So 10% or 0.1 for that proportion corresponds to that 1.28. Does that make sense?
Oh, you check the tail to get 10%.
Yes, exactly. Yeah,
But
anytime.
why the tail and not the body?
Because we want, so I mean, you could, in theory, do essentially the mean to z in here. But let me go ahead and share a screen one more time. So if we have our distribution in here, we want the value that corresponds to the middle 80% in here. If we got this value and said, okay, what is 80% in the body? That would leave us 20% in this tail. And that's not what we're interested in. We're interested in what is the middle 80%. So we're excluding the extremes, right? We don't want these areas over here. And so what we do is find, okay, what is the single value here that would give us the desired 10% over here? And that when we make it negative, gives us the desired negative, or gives us the desired 10% over on this side. Does that make sense?
Not really, because I don't know why you're concerned with the 10% when you're supposed to be concerned with the 80%.
Yes, so we know that the full distribution in here represents 100%, right? And we know that we want the middle 80%. If we want the middle 80%, what's on the edges here has to be equal to one another. Right? And so if we have that 100% minus the 80%, that leaves us 20%. And we know we need two tails here, two tails of equal probability. And so we take that 20% and we divide it by 2. And so that gives us 10% in each tail. So we know if we get a z-score that corresponds to having 10% in each tail, what's left is this 80% in the middle.
Okay.
Does that help?
Yeah, sort of.
Okay. If not, I'm more than happy to set up a meeting and we can talk about it face to face. I know it is a kind of confusing concept here. And so it just kind of takes thinking spatially of if you have 100% represented here and you want something in the middle, what needs to be equal on the outsides to allow you to get that middle point? All right. So let's go back here. Yeah, where'd you go? All right, so let's come up with another example here. The mean SAT scores for one sample of 100 students was 471. Let's assume that the population mean SAT is 455 with a standard deviation of 100. What's the probability of selecting a sample with a mean greater than 471? So let me go ahead and once again. All right. So we know that we want the probability of a sample with mean greater than 471. And in this case, we know that the SAT has a population mean of 455 and a population standard deviation of 100. So, what do we need first?
The z-score, or
Yeah, so we're going to have to find that z-score. And what's the equation for the z-score?
hold on. The oh boy, x minus mean over standard deviation. I think
Yeah,
so.
so that's what we have traditionally been using. And
Or
for
the unit table, right?
well,
what we
yeah,
do?
so that's what
Mhm.
we've gotten. That's how we get the z-score, and then with the z-score, we find that probability. But this is the equation that we have been using for just a single value, right?
Is it
Oh, over the standard error.
Yeah, and so
Mean
this time,
minus
mean minus mu?
mean minus
Yeah.
mu, exactly, over the standard error of the mean. All right, so we know we've got our mean. We know we have our population mean, but we don't yet have the standard error of the mean, right? And so what's the equation for standard error of the mean again?
Standard deviation divided by the square root of n.
Exactly, yeah, standard deviation divided by, whoops, jumping the gun here. Where is it? Standard deviation divided by the square root of n. So we know our standard deviation is 100. 100. We know that the number of people in this sample was also 100. So it gives us 100 divided by square root of 100, or 10, which gives us a value of 10 for the standard error of the mean. So now if we go back and look at our equation to get our z, we need that mean that we're interested in, so that 471. So 471 minus the population mean, right? And that population mean is 455, divided by the standard error of the mean that we calculated as 10. So that gives us, let's see, 16, is that right? 16 divided by 10, or 1.6. So our z-score is equal to 1.6. And so now if we take that value, and we're going to go look that up in the unit normal table. We're looking for that z-score of 1.6. And are we interested in the tail or the body percentage?
The tail.
Why?
Because we're looking for the proportion that's greater than 471. So we want what's above z.
Exactly. Yes. And so we look at that probability, and that's 0.0548. So now, excuse me, now if we go back to our table, and perfect. There it is. Awesome. Questions about that problem?
So we used the z equals mean minus mu over the standard error of the mean because we were looking for the probability of the mean instead of just like the probability, right?
Yes, we were looking for the probability of selecting a sample with a mean greater than 471. If this said, what's the probability of selecting a single person, then we would use that old equation of the x minus the population mean over the standard deviation. But because we're interested in what's the probability of selecting a sample of 100 people, 100 students that have a mean greater than 471. That's why
Okay,
we
so
use that
we're
standard.
looking at a larger, what, distribution of people, I guess?
Yeah,
Or,
exactly.
okay.
Awesome. What other questions? Awesome. All right, let's work one more example. And I tell you what, I'm going to have y'all start working this on your own so you can try to get the practice, and then we'll work it together. So go ahead and spend a couple minutes trying to work this, and then we will do it together. All right, take an extra minute or two here. It is, Caleb. We will go over that, everybody, here in just a second. Good work. All right. So this problem is asking us to essentially establish what is the probability of obtaining a sample with 100 people that has a mean of 68.4 on a given test, right? And we know a couple things about this test. We know that it has a mean of 65, and that has a standard deviation of 20. And so what do we need to do first?
Find the z-score.
Well, so yes.
And the standard deviation. Not standard deviation, the standard error.
Yes. So we do need to find the z-score, but to get that exactly, we need to find the standard error. And so the equation for the z-score that we're going to be using is the sample mean minus the population mean over that standard error of the mean. To get that standard error of the mean, we again have to take the standard deviation, in this case 20, divided by the square root of the number, and in this case, that's 100. So we know that the standard error of the mean is going to be 20 over 10 or 2. Right? And so now, given that, we can find our z-score by saying, all right, we know what the sample mean is, 68.4. We know what the population mean is, 65. And we're going to divide it by that standard error of the mean, which in this case is 2. So we get 3.4 over 2, or that equals a z-score of 1.7. So now, once we've got our z-score, we can go look it up in the unit normal table here. So let me pull this up in the unit normal table. So we're looking for a z-score of 1.7. And are we looking in the tail or in the body?
So,
Tail. Yeah, why tail?
because we're looking for the probability that's above where z-score is.
Exactly. Yep. So we look above that z-score or in the tail, and that probability is 0.0446, or about a 4.5% probability, right? And so now we can say, okay, the fact that the researcher obtained the sample that had a mean of 68.4, that only had a 4.5% chance of happening. Right. And so now that's where we start getting into the ability to attribute other potential explanations. So maybe the sample was, a sample of UAH students who are uniquely brilliant, or maybe, he gave them some sort of study procedure to go through, and that started to help. But now you can start to see how we're able to get the probability of something happening based off of a known population mean and standard deviation and a sample size. And so y'all can play around with this now. You can start thinking about, okay, what are things we have a known mean and standard deviation of? You could do things with IQ. So given IQ, having a mean of 100 and a standard deviation of 15, what is the probability that we select a group of 100 students or 25 students or any of these numbers that have a mean IQ of, let's say, 107 or greater? And then you can go out and figure out what that actual probability is. What questions do you have about what we covered today?
Can you go back to the definition of standard error? I mean, like just what it means conceptually.
Yeah, absolutely. Let me pull up the slides here. Yeah, there we go. So again, it is just that standard deviation of the distribution of sample means. So you have your population, you pull out 25 people, you get their mean, you put them back in. You pull out another 25 people, you get their mean, you put it back in. And you do that a whole bunch, and you plot each one of those means that you get. And the standard error is just the standard deviation of that new distribution of those means.
So it's like the standard deviation of a larger group in a way.
It's the standard deviation of a group of means.
Okay. Gotcha.
It's essentially saying how far away is every individual sample mean from the population mean.
Okay.
What other questions do we have? All right, so next time we are doing our test review. We're going to do it all virtually here so that everybody gets the exact same experience for that test review. Come with specific questions. So you should have already studied by the time we do the review. I'm more than happy to answer specific questions. But what I want to avoid is somebody saying, can you go over the entire lecture on z-scores again? Because I want it to be very specific and targeted. So if you decide to show up for it, bring specific questions. Yeah, I will hang out here until everybody has signed off. And have a good weekend. I will see y'all next week.